Hello, everybody. My name is Patrick Galbraith. I'm going to talk about complex stateful applications made easier with Kubernetes, aka MySQL on Kubernetes. This is similar to a talk I gave at KubeCon this year. I've custom tailored it to the audience. Many of you might not be avid Kubernetes users quite yet. I hope to change that with this talk. A little bit about myself. I've been around doing this for a while. I first met Monty Videnius in 1999 at a company called Andover.net, and we needed this feature for Slashdot called replication, so we paid to have them develop it and sponsored that. And that hence began my time with working with MySQL. It's been about 20 years now. Well, actually before that. So I work for Oracle. I work on the MySQL as a service team. We're building a database as a service based off of MySQL 8.0 running on Oracle Cloud. It's really going to be an excellent product. We're still in development phases right now. We've had internal releases. We do plan to have a self-managed ease of use service. It's going to have APIs, CLIs, software development kits, seamless integration, elastic, HA, replication across physical locations, security and compliance, all of that built in there. That's what keeps me busy, as well as my working with Kubernetes. So what is this presentation about? So this presentation, one of the things I've noticed throughout the years, and it's becoming less so now, is there's kind of this misconception with containers and using them for databases. People think that maybe they're not suited for databases. And that is quickly changing, as you can tell with the numerous operators for MySQL that are now available, as well as Mongo and other databases. Containerized stateful applications, and in particular stateful sets, how that's made it much more easy to run databases on Kubernetes, and actually, and in fact, Kubernetes makes it easier to run a database, and it's much easier now. MySQL running on containers, as well as MySQL running on Kubernetes specifically. Also need to discuss the operator pattern, what that means, and in particular, the Oracle MySQL Operator. If we have, depending on time, this is a bit of a kitchen sink of a presentation. We'll go into talking about Vitess and what that is. I have a demo for that. I have a demo for the operator, but there's probably only time enough for the one demo. And it's a recorded demo because doing live demos at conferences is tricky because of the Wi-Fi and also the mistakes that happen when people are watching. So feel free, you can, I have saved questions till the end here. You're welcome to ask a question or two during the way to kind of help guide me along if I'm kind of going off on a tangent. So here's a bit of a container refresher. What exactly is a container? When I first started using containers, I had kind of the approach, and I think a lot of people do, that containers are somewhat like virtual machines. And after years and years of using them, I now realize they're completely different, similar use cases, but they're completely different way of approaching it. In that, with a virtual machine, the virtual machine has its own operating system, a full install, and there's software that runs on the bare metal machine that runs the hypervisor that runs the virtual machine, whereas containers run within the OS. They're OS features. They're made possible with kernel features such as kernel namespaces, PID, IBC, mount, network, and user. C groups, those are control groups where you can limit the account and isolate resource usage. And these are features that have been in Linux for quite some time now. Google really is the pioneer in using containers on Linux. There are containers for Solaris for the longest time, BSD jails. And what has happened recently, what's happened in the since Docker's come about, is Docker made it possible to use them, much easier to use them than before. They have kind of this whole package where you can interact with the container and utilize it. You can specify what kind of networking you want it to have, what kind of volume mounts you want it to have, and it's essentially brought containers to the masses. So this is a graphic that I like to use to kind of get the idea of what the difference is between containers and virtual machines. With a VM, you can have whatever number of applications you're going to run on there. And each one of those virtual machines has their binaries and their libraries, as well as the guest operating system. And when you bring it up, you have to boot up an OS, and it can take a little bit of time. Whereas with a container doesn't have that hypervisor layer, and a container consists merely of the things that are required to run the application. You can think of it almost as a package, but with extra, with all the requirements satisfied. You don't have to deal with dependency hell of trying to manage it. You don't have to really use something like Chef or Ansible to manage the container itself. You can use it to run the container, perhaps, but it's not the same as a hypervisor. And it comes up much faster, and the images are much smaller because they do only consist of what's required to run it. In MySQL case, that would be essentially what you would have in your MySQL installation directory. And then, of course, your data would be on a volume. And so you don't have this extra layer with the hypervisor, as I mentioned, and it's much faster to run. And then what Docker does is it makes it possible to interact with those containers. So here are some points, VMs versus containers. As I mentioned, the VMs require a OS installation and a software emulated machine versus containers, which are merely isolation, and they only include the application. VMs provide an abstract machine, whereas containers provide an abstract OS. Virtual machines have a hypervisor emulation layer. Containers are more about isolation within the OS. Virtual machines generally have a longer lifespan than a container. Containers are more of the pattern of you have a life cycle where versus pets versus cattle. Virtual machines have their own file system and interact with external storage like a real machine, whereas containers you have generally an ephemeral disk. It's part of the operating system that it's running on, and it's comprised of different layers that make the container distinct. Oh, great. Why is it doing this to me? Oh, okay. So they're made up of layers, and you can specify external volumes on the container on the host OS. Virtual machines networking is specific to the virtual machine, whereas containers, it's through Docker, or if you're using Kubernetes, it's done through the Kubernetes system. Virtual machines are more secure and more isolated than containers. Containers, it is running on the OS, and on the OS you can view the processes that are running within the containers. Whereas with a virtual machine, you don't know what's on your host machine, you don't know what's running on those virtual machines. A host, as I just mentioned, it can't see the virtual machine process, but actually I misworded that. So the virtual machine can't, the host can't see the VM processes, but the host can see the container processes. So there was always kind of, I've noticed with a lot of customers that I've spoken with and people that I've spoken to, oh no, we don't want to run databases on containers. That's, one of the first things you see when you read about containers or Kubernetes specifically is that pods are mortal, containers are mortal, and that's not something you want to hear when you're talking about a database. That's true, but when you think about a database, the container could be disposable, but it's the data itself that's persistent and lasts throughout restarts of the container. So it's a bit more of a conception than reality. And containers actually make it simpler to run any application, because if you're developing your application and you know your environment works on that container, you can be fairly sure that that container you ship is going to run the same as you want it to run anywhere else, because it has all of the the prerequisites of running the application, the libraries, everything. And there's no emulation layer, so you don't have to deal with the overhead of that. So if you're running on a bare metal machine, you're going to pretty much get bare metal performance. So database. A database, this whole question of pets versus cattle. Databases tend to be much more pets than cattle. Our databases, it's our data. It's the most important, I would say, the most important part of the entire stack. Applications come and go, they run, but they need the database for persistence. They need that data that they're going to serve up. So they're long lasting. A pod of multiple database instances or one. When you read a description of a pod, it says one or more containers running on a machine. Now with a database, you don't necessarily want to have multiple pods of the same database running. So the question in your mind then becomes, well, what does this mean within Kubernetes? Originally within Kubernetes, we didn't have stateful sets, so you had to do tricky things like I did an example demonstration. It was using Percona XtraDB cluster. And what I did is I had a one container pod that I would run on each machine, and it was named, database 1, database 2, and database 3. And you had to really think through as how you run it. It's no longer that way, and I'm going to demonstrate that with stateful sets. A database is also a very complex and stateful application. It's something that, there's a lot of tuning that you can apply to it. It requires a lot of resources, a lot of I/O. So it's something that, people, when they hear about containers, they're a little bit anxious about. Database, you want stable access. You want to get the same database handle. Networking wise, what that means is you want your application to always be able to connect to the database and get that consistent access point. What else do you want with databases? You don't want to scale if the database is unhealthy. If you have, for instance, you're building up a cluster, a 3-node cluster, you don't want to keep scaling if the second node has a problem when it's coming up. And most importantly, you want some persistent storage. So what does this all mean within containerization? And what does it mean for database containers in general? So the containers are the cattle. They come and go, but the data itself, running on your persistent disk, that is the pet. So you can almost say that databases can be cattle, but that the data has to be the pet, and you have to treat it as such. So you need something that's going to make it so that container, if that container goes and the same image restarts again, that it gets the same data as before. So here's kind of a graphic that I have where I talk about the pet. This is the data. And then, say for instance, we're using Kubernetes. We have secrets and config map. These are kind of persistent type things. They're not the actual data, but they're important bits of data that the database needs. Config map is where you would store your configuration for the database. And then you have the container come up. The container has the MySQL binaries, the libraries, and then it also has a directory structure that it then mounts to the config map, as well as the persistent, if you're running block storage in the cloud, you want it to mount to a particular location. That can die, but then when it comes back up, you want it to assume the same things as before. And in essence, it still runs like it's the same thing, the same exact thing that was running before. So Kubernetes is, as we saw in the opening today, Kubernetes really is becoming the de facto cloud platform that people are running applications on. And that's because it really makes it easy to, number one, run a cloud, number two, run applications in the cloud. And it's also an open source project, which means there's thousands and thousands of people working on it, thousands and thousands of people trying to solve the same problems you're trying to solve every day. So that's a really good thing. And it's constantly moving. It's a moving target. Tale of two open source projects. You have MySQL, which is the world's most popular open source database. It's ubiquitous. It's been around 20 plus years. And then you have Kubernetes. Kubernetes is a pretty new project. It's based off of technology that's been around a while. Kubernetes was based off of Borg, which is what Google uses to run containers. And it uses the same patterns that Kubernetes is built off of. When Google decided to release Kubernetes, they wanted to take some of these best practices and introduce them to the world and build a project that did these things. Everything that Google runs is within a container, and that has been that way for some time. So the goal is to have something like that, but that everybody can now use. It's the fastest growing open source project. Every year, if you go to KubeCon, the conference doubles or triples every year. The first year, I remember it was maybe 1,000, and then the year after that, it was 2,000, and then 5,000. So it's a pretty amazing project to see. It's application deployment done right. When you deploy an application in Kubernetes, you don't have to deal with, it's a pattern known as immutable infrastructure. Traditionally we've had resources. In the old days you had a sysadmin. Sysadmin had to set up a database, set up applications. When we ran /dot, we had hardware machines. We hosted them in the data center somewhere in Lexington, Mass. We had to go and wire the cabinet. We had to install MySQL. We had to make sure the application boxes were set up. We used NFS to mount a common directory across all of them. And we also had to make sure we knew exactly where the database was. That was difficult. That took a long time. And then it evolved to things like Ansible, Puppet, Chef, SaltStack, CF Engine. And that made it possible to now be able to go in and manage lots of machines. But you're still basically managing machines. But with immutable infrastructure, the idea is that you use something like a container. The container has everything built into it. It's pre-baked with all of the good things you need it to have. And then the system, like Kubernetes, what it does is it brings up that application and makes a few adjustments that are necessary for it to run. And if something happens to it and it's thrown away, you don't have to bring it back up and then run Chef or something like that. There was a system that I most recently managed prior to moving to this group, and it runs DNS. And it was a system that was written prior to Kubernetes, and it had all of these things that it was cobbled together with, namely Chef. It had containers that came up and ran Chef and did all this provisioning, and it would take some time to do it. Kubernetes is not that pattern at all, and you don't have to deal with that anymore. So as I mentioned, it's community-driven. It's a moving target. One thing to understand with Kubernetes and containers in general, or anything in that ecosystem, is it's going to change. So in your knowledge, you have to keep on top of the knowledge. Just doing these talks, I have to check my notes before I give it because something might have changed since I finished the slides. And as I mentioned, the Borg project, there's a link here on the slides, and the slides will be available. It's a really good paper to read to kind of understand kind of the thinking as to why Kubernetes came about. So here's some Kubernetes ingredients for running stateful applications. I'm at almost 20 minutes here. Good. First and foremost these are what I think are important, labels. Labels are key in Kubernetes. What a label is at the basic level you have a pod, and say you want to label your pod database. That label is something that then an application can utilize in a label selector. Labels are kind of an identification system within Kubernetes. Think of it as discovery information. Say, if you use Chef, there's Ohai. Ohai kind of lets you see what's on the machine, and you can query the Chef server and see what all your machines have installed. Labels are part of that type of information. Or Ansible, if you do Ansible facts, you can look at what your machines have and what you need to tweak. This is all inside of the Kubernetes system, which is great. And furthermore, a lot of what's in labels is also surfaced through Kubernetes DNS. Kubernetes has its own internal DNS system. So things like a database, you can refer to it within Kubernetes through a domain name. And it's not a domain name like .com, it's within Kubernetes. Pods, services, and volumes. Pods, I mentioned, of course, pod is the basic object within Kubernetes. A pod is one or more containers running on a machine, and it's declared with, you can do it in JSON, but most of the time people use YAML, which I prefer myself. Services are a stable network access point. Through restarts, that service will point, using a label selector, to the underlying application that's running. Say, for instance, you have a service for a database. It says port 3306. This is how I'm going to connect to the database on this host, and that's how that works. Volumes are a way of declaring some sort of disk resources, whether they're block storage, whether they're NFS volume on the host, whatever it is you want, mogul FS. Btrfs are a number of ways of doing Ceph. kubedns, as I mentioned, I won't go into that. That's just Kubernetes DNS system. Helm charts. Helm is like a package manager for Kubernetes. It lets you install applications within Kubernetes. Persistent volumes, persistent volume claims, and storage class. Persistent volume is just an area of storage that you say is a volume that's available to use. Persistent volume claim is the claim that the application makes. So your database makes a claim against some persistent volume you've declared in block storage. Storage class. Storage class is another abstraction on top of that. And storage class says, if you're using a stateful set, which I'll describe further, you say I want 20 gigs of this storage class called OCI. It's Oracle Cloud Storage. It'll automatically create a persistent volume and then a persistent volume claim for that pod. Stateful sets. So most applications that are ephemeral applications use what's called a deployment. Deployment runs replica set, pods, and it takes care of scaling. You can specify how much you want. You can change how many replicas you want running. It's great for ephemeral applications, not so great for databases. So what was developed is a stateful set. They originally called pet sets, but what they do is they allow you to define, for instance, say a cluster. You say, I want to run this cluster, and the way it runs it is it'll run each pod in ordinal order. So say, for instance, you have your stateful set called MySQL cluster. The first pod will be MySQL cluster -0, -1, and then -2, and then so on and so forth. And everything named with that pod will have a named value, a canonical name. So your volumes are associated with that pod, network. Everything will be sticky across restarts, which is a really good feature with databases. As I mentioned, we want the container can go away, but we want it to come back up and assume all of the same aspects that make it that thing, if that makes sense. Operators. Operators is another abstraction. An operator, you heard it discussed this morning in the opening, in the keynote. Operator lets you extend Kubernetes. You can define custom resource definitions. And this allows you to create new resources, say, for instance, MySQL cluster, or Percona cluster, or Mongo cluster. And it lets you interact with Kubernetes in such a way that you can work with your MySQL cluster instead of thinking of it as pods. And it takes care of it, has all of the domain knowledge. You know, your DBAs, your developers, you know how to do all of these things. Many of you might have gone to tutorials yesterday to see how to set up group replication, InnoDB cluster. All that expertise is built into an operator so that you don't have to think about how to do it. So it makes it easy to build up a cluster, and you'll see that. Sidecar containers. Sidecar containers are just a pattern. They're essentially containers you run along the main application container to do tasks for you. Node selector lets you specify affinity for a given machine. So you might have a cluster, a Kubernetes cluster with, say, 3 machines, and maybe you have 2 of them that are well suited for running a database. So node selector lets you make it so that you can specify affinity for certain applications to run on certain machines. Here's kind of a diagram. It's a bit hard for me to see. I don't have my glasses on. But Kubernetes, you have a master, which consists of the API server. It has a scheduler, a replication controller, and then each node that runs the containers is called a minion, and it runs kubelet and kubeproxy. Kubelet takes care of running containers. Proxy takes care of dealing with the networking layer. I'm sorry if I'm going a little bit fast. So this was one of the first. I did this example for Kubernetes when I first was trying to get familiar with it. Databases help me to understand things. So I was trying to figure out how would I run MySQL on Kubernetes. So I came up with this example in their example directory. They've since moved it out because there were so many examples people contributed. But this is essentially showing you how you had to specify. You would create a replica set, and you would call it PXC node 1, and it's just one container, and you'd have to specify all this information. So all of this pain and suffering is now taken care of because now you have stateful sets, operators, and I'll talk about that further. Helm, here's, I don't know why this slide is here. I won't go to the node selector. This is just This right here talks about the affinity. As I mentioned, you can say I want to specify what box type I want something to run on. So the image is MySQL 5.6. Say I want it to run on that, the box type C3 medium. And you would have labeled your nodes earlier. You can label anything in Kubernetes, including the nodes that it's running on. And that's how you would do that. And here's just kind of some examples of affinity and anti-affinity, which is great because it gives you just so much control of how you can run things. Stateful sets. This is the thing I really want to get to. So what they do is they provide guaranteeing about ordering and uniqueness of pods and pod resources. They maintain persistent, sticky identity for each of their pods across rescheduling, across restarts. They ensure ordinality. This is really important when you're bringing up something like a cluster. You want it to come up in a very specific order. With a deployment, you can't do that. At most, you have one node per index. I see a question out of the corner of my eye. Oh, sorry. I don't know why it's doing that. It's really, I want to throw it out the window. There's no window. Stable network identity across restarts. This is another really important thing. So when you use a stateful set, there's so much to talk about. You have your system, your cluster, it's called MySQL in this example, and you create what's called a headless service in Kubernetes. What that does is it creates, think of this as like this is the domain name, and then that's the host name. So each one that comes up, it's node-ordinal.domain. DNS is stable across restarts. It also gives you stable storage and stateful resources. Pods remount the same persistent storage across restarts. Safety. If the cluster is unhealthy, it's not going to scale. So here's a good example. I like this. I learned how to use PowerPoint this way. So this is a replica set, how it works. So you have your replica set. Say you called it MySQL. And this is how it would run things. No particular order. And if you look at the name, it's the name of the deployment dash the deployment ID dash a random 5-character string. And that's fine for ephemeral applications. Oh, and if it crashes, it keeps going. This is great for ephemeral applications, terrible for databases. Where the stateful set, you have your stateful set called MySQL. First node comes up, MySQL-0, -1, -2. Something happens, we're going to replace that node. And if we were building up the cluster, it's not going to scale past the one that's broken until the one that's crashed is brought back up and the problem resolved. So the headless service, this is what I mentioned earlier. So a service is, again, a stable network access point in Kubernetes. And this one, you don't use it for accessing the database. What this is for is this is a bit of a placeholder. And what you're saying is the name is MySQL. It's a cluster IP of none. This basically says we're not networking with this one. I mean, you can say what port it has. And then over in your stateful set, you say it has a service name of MySQL. And what that does, as soon as it sees that, when it brings up the stateful set, when it brings up the nodes, it's going to create DNS entries for each of those nodes. So you can then refer to them in your application by the domain name. So storage class and volume claim template. So in this example, we have we have a storage class definition. It's a bit busy, but just say the name is OCI, provisioner is oracle.com OCI, and it sets up storage, block storage for you. And then within your volume claim template, which is in your stateful set definition, you say, and you have an annotation that says what my volume is. I want to use OCI, storage class name OCI, and I want 50 gigs of it. So what it's going to do automatically, each one of those pods that comes up within the stateful set is going to create a volume claim for that and a volume for it. So if you want to understand how stateful sets run, this is a really good definition, a really good pattern right here. I'm looking how much time I have. I'm doing good. So this is Anthony A. created this. This is not something you'd use in production, but it's a really good idea to hammer home the pattern of how stateful sets work. And this is regular asynchronous replication example. And what it does is it shows you, first of all, you have your first node. That's going to be your master. Then subsequent nodes will join up and be slaves off of that master. And it shows you how it sets up a read service, a headless service, and it also shows the pattern of it is really, you'll see a lot of this out there in many more complex permutations, but this is the basic pattern of how you would use MySQL on a stateful set. You have your config map. Your config map contains a master.conf and a slave.conf. And the way that works is it uses the ordinal value of determining which of that it's going to use. So the first pod that comes up is -0. If it's -0, what it's going to use is going to use master.conf. Secondly, what it's also going to do is you're going to have init containers. So you have an init container that takes care of mounting the config map, and then you have this other init container, and what it does is it clones MySQL. If it's ordinal -0, it clones the database and then has ready on a port a backup ready to give to the slave that subsequently comes up. So if it's ordinal greater than that -0, it's a slave, and it's going, that init container, instead of making a backup, is going to receive the backup and restore it. And so on and so forth. It'll just keep coming up. Also in this, you see here, there's varlib MySQL. This is a volume. It shows how volumes work. It also shows how the backups work using a sidecar backup container. There are a lot of operators that use this pattern, and they don't use it in such a simplistic setup, but this gives you a really good idea of understanding how MySQL runs on Kubernetes with stateful sets. Operators. So as I mentioned, wow, that's really irritating. I'll just have to sit here and move the mouse continually. So it's an application-specific domain controller. All your domain knowledge for a given application is built into that operator. They're written in Go. They are done using the Kubernetes API, and they extend the Kubernetes API. And the way they work is usually you have a pod that consists of the implementation of the operator. And what it does is it connects to the Kubernetes API and watches for the custom resources that are requested for that type of operator. For instance, for the Oracle MySQL Operator, it watches for MySQL-cluster resources, MySQL backup resources, and it'll act on those. It encodes application-specific domain knowledge. I've talked about that. Everything you know as a DBA or as a developer of that application, it builds that into there so that a lot of these repeatable patterns you're continually doing on a regular basis, it's built in. And it enables users to create, configure, and manage stateful applications. As they mentioned this morning, they have the extra DB Galera operator for Percona now. Setting up a Percona cluster, you can do that through the operator. You don't have to manually set it up like you did before. The MySQL operator, which I'll show you, it sets up InnoDB cluster and group replication. So all of the things you normally would do to set up. There was a tutorial yesterday by my friend LeFred and Kenny Grip, and it was pretty, they showed how to work with group replication and how to run this. And you could understand and get some appreciation for what's involved in doing that. The operator has all of that built in. So within 5 minutes, you can have a cluster up and ready to use and break if you choose to do so. It allows users to create, configure, and manage stateful applications. It's built upon resources and controller concepts. This means that it uses Kubernetes resources like pods and stateful sets, and it has a controller that goes in a loop and looks for things that it has to act on, MySQL backup or MySQL cluster or MySQL restore. And as I mentioned, it leverages Kubernetes primitives like the replica sets, stateful sets, and services. Operator executes common application tasks. Generally, they're installed as a deployment. Some are installed through Helm charts. I noticed that the Percona one is installed just by running the YAML files. The custom resource definition types for operator can be anything that you want them to be according to what you're building. etcd cluster was the first one that was developed. That was developed by Red Hat because etcd was a little bit of work to set up. Prometheus, MySQL cluster, backup, restore, Oracle WebLogic. Every day there are new operators, so to try to list them here is kind of a fool's errand. Operators, the way they work is observe, analyze, and act. That's the basic pattern. So just think of it, the first thing they do is they observe the state of something. Say, for instance, we have the etcd operator. There's going to be 2 running pods. The first one, etcd3, is version 3.1.1. etcd1 is version 3.2.10. Differences is from the desired config. We're going to analyze that. They should be 3.2.10, and they should have 3 members. How do we get to the desired config? We have to, first of all, we have to recover 1 member, and we have to upgrade etcd3 to 3.2.10. So then it acts, and it does that. At the bottom of that, you'll see a link. I'd love to show that, but due to time, and it's a pretty short demo, but it gives a really good example of how an operator works and how it deals with, thank you, how it deals with having to deal with a failed node, how it deals with doing an upgrade and getting it to this desired config. MySQL operators. These are 4 of them that I know of. Actually, 3 of them that I know of. There are some more out there, I'm sure now. But the ones that I'm most cognizant of are Oracle, which is the one I'm going to demonstrate. Then there's also the Percona one that was announced as GA today. And then there was also one done by a group called Press Labs. They're a Romanian company that builds WordPress websites. The Oracle operator uses InnoDB cluster and group replication for its cluster that it builds. Percona uses ExtraDB cluster. And Press Labs uses a pattern that is quite familiar out there that GitHub uses and many others. I think Booking.com also uses it. It's where you run semi-sync replication, but you use MySQL Operator, which is an open source project by Shlomi Noach, and it essentially manages a cluster of a master and some slaves. And that's built into the Press Labs operator. It's pretty cool. It's great that there are all these options for running MySQL. I'm going to delve into particularly I work for Oracle, so I'm going to talk about the Oracle MySQL operator. This was released about a year ago. It's available at the GitHub address listed here. And what it allows you to do is deploy a highly available clustered MySQL instance into Kubernetes with a single command. It washes the API, as I mentioned, for custom resource definitions for MySQL cluster and acts on those resources. The custom resources that it makes available are backup, schedule, and restore custom resources. It's very prescriptive, meaning, MySQL 8.0 is what it utilizes to do this. As I mentioned, it utilizes group replication, InnoDB cluster. So when I say it's prescriptive, what I mean is it's a very specific way of deploying MySQL, and it's built into that operator. It also allows you automated backup and restore from object storage. The way that the operator runs is you have the MySQL operator. It talks to the Kubernetes API. It watches for those custom resources, and it runs whatever number of pods within a stateful set of the MySQL cluster. All these bullet points apply. I won't, limited time. And this is what an operator pod looks like. You have an agent, which is your sidecar container, and it talks to the MySQL container and manages it. It also runs backups. It takes care of building the cluster. And then it runs those backups. It streams them to object storage, which is an S3 compatible API. When it does a restore, it streams it back from object storage. And these are the custom resource definitions: MySQL cluster, backup, scheduled backup, and restore. Scheduled backup is a bit like a cron job. So here's a simple cluster. Essentially, to create a cluster, cube control apply -f, whatever your cluster YAML file is, and then you can list clusters. Here's the most simple pod file over there, API version v1 cluster. That's it. There's also another value in there. This one's a little bit more, let's see, what do we have here? We have backup. This is a backup. To make a backup, it's as simple as running a YAML command, and then you can list backups, and then you can fetch an individual backup. You can also run a restore. And I'll hurry up here so I can get to the demo, because the demo is pretty cool. Here's what the backup looks like. Right now, we support MySQL dump, but we're also building functionality for enterprise backup, as well as we'd like to do extra backup as well for that. The operator is extendable. And this also says what the S3 bucket that it's going to go to, what region it's in, and what the credentials are, which are stored in a secret. And here's how a restore works. But scheduled backup, the difference with this is that it lets you specify a schedule when you run with a cron type string. Same values as before, the S3 endpoint. And how you connect. So you can, several ways you can connect. You can have a write-only service where you pick an active node to write to, a read-only service where you can write to any one of the, read from any one of those. A better pattern is to use MySQL router, which is cognizant of the state of which is the active and which are passive within the cluster, and it routes accordingly. And usually with that, you run that as a sidecar container with your application 5. Okay, I'm going to get to the demo. Yeah, I knew this would happen. All right. So this is our initial state. So we have, we're looking at our namespaces. We're going to create a we don't have any Helm charts running. We're going to create a namespace called MySQL Operator. We're going to install the operator. We can now see the operator's running and it's ready to go. I might have to zip through. Oh man, this is not displaying nicely. So, I'm sorry. So, this is really frustrating. Let me try to escape from this. Okay, this will work better if I do it this way. So what we have here is we install the operator. And then we're going to start looking at the logs of the operator while we run things. Here we specify, we're going to specify how we run our cluster. So we have a config map. We have a secret for the root password. We have a cluster, 3 members. You can see right here it's 3 members, and we're going to say what the configuration. This essentially mounts a config map which specifies some values for what our configuration is going to look like. Right here, we kind of override the default configuration, default authentication plug in MySQL native password. And over here, we create a service account. Service account is so that the agent can manage the actual underlying MySQL containers. So we have the operator running. So now we created a namespace. We're going to run this. We're going to use this namespace for running our cluster. So we're going to create our cluster. I'm doing this manually so it goes by a little bit faster. So now what we're going to do is we're going to watch it as it comes up. So you can see the first one comes up, -0. And over here we're going to tail the logs. We're going to watch which persistent volumes become available. And this will kind of let us know how fast things are coming up. You can see now that the second node is coming up. We're going to look in Kubernetes really quick to see what is going on within Kubernetes. We can see that things are beginning to come up here as well as in this UI. I generally prefer to use the command line, but some people like to use this. So now we can see the final pod is coming up. And when that's completely up, now it's 2 of 2. We have a running cluster. And you can see over here now all of our volumes are bound, so it's ready to go. So what I do now is I tail the logs for each individual pod. And you can see, the reason I do this is so you can see backups when I run backups. So here's a WordPress deployment. This is the WordPress app router. This is a container that runs, it's a proxy to the cluster. And then this right here is we say it's a load balancer. What this is going to do is it's going to use Oracle Cloud's load balancer service to create an external access point. It's also going to add a DNS name kubernetescluster.com, so we can access that for our application. And then here's the application. This is the WordPress application, and it's going to talk to MySQL router, localhost, and these are the user, port, and host. And you see it's 127.6446. That's because it's a proxy, and since we're running within this pod, two containers, they're in the same pod, so they essentially work like localhost. So here's external DNS. We're going to run an external DNS. What that does is it watches for any annotations specifying DNS names, external DNS, that is. So if you create a load balancer type service, what it does is it'll create a DNS entry, and we can access. We can see now that this is already running. We're going to create the deployment. Now, you see WordPress is coming up. We're going to look at, I think the next thing we're going to, okay. Sorry, I'm going so fast. I really apologize. So that application is running. Now we can access it as kubernetescluster.com. So now we have a WordPress website. We're going to install WordPress, set that up. So now we have our first hello world. This is a stock site. So the first thing we're going to do is we're going to make a backup. This is backup-1. S3 credentials, we're going to send it to MySQL Backups. And it's in Phoenix. We're going to create that backup. We have to create object storage credentials, obviously, too, to talk to object storage. So now we're looking at the logs. As I mentioned, you can see the logs of where the backup's being made from. So it's going to run it from a secondary node. You can see right here from the text from WordPress-2, the log, the Kubernetes log there. You can see that the backup was made there. Now we're going to customize it. I kind of speed this up. The person adds a bunch of posts to it and sets up their WordPress customizations, their themes, all of that. So now we're going to create a second backup. And we just copy the first one and we name it differently. Oops. So let's see, WordPress backup 1. Sorry about that. Now we're going to make a second backup. This one's called -2. How much time? 1. Okay, I'll hurry this up. So we make a second backup. We go into the database. We connect to the database. We truncate a table. Oh no, the site doesn't load. So now we do a restore. And it's restored. We have our site back. And it was that easy to do that, where our site's back and running. And that all takes to run a website, to run a cluster, to bring all that up, it takes about 10 minutes. Back in the old days, that used to take days to set all of that up. So Kubernetes makes it easier to run databases. That's the whole objective of this discussion, that things that used to be manual and you have to do a lot of manual steps to run it used to take a lot longer, and now you can do it with a single command, and that's why Kubernetes is, in terms of stateful applications, is really caught on fire. There's Josh Burkus. He did the Postgres operator, by the way. That's a really nice piece of software. So do you have any questions?
Are we going to get the slide share?
Yes.
Okay.
I'm sorry for the time constraints.
We don't run the video.
What?
When you do a backup,
Yes?
how do you connect to the node?
Oh, that's all done through the operator does that for you. It streams it to, when you do a backup, it picks a secondary node to run the backup from, streams it to the S3 API, and then when you do a restore, it streams it to a primary node.
Right. And what I'm talking about is you have a master node
Yep.
and an async node, let's say for a reader, right?
Mm-hmm.
So how does the operator know which part to back up in case it fails over?
The operator has all of the domain knowledge, as I mentioned, built into it that knows how to pick a node to do a backup from and to restore to. The operator says, I have to do a backup on a secondary node, so because within Kubernetes you have a view of what's running and what type of nodes they are.
So